Good morning, everyone. So my name is Aseem Sharma. I'm from Corero Network Security. I'm the Security Services Manager over there. And I'm here to talk to you about the threat of multi-vector DDoS attacks, their implications and some considerations for the NOCs, defending against them in 2019. Now, what I've done here is I've used an example of a recent DDoS incident that occurred at one of my customers just a few weeks back. Okay. So what I've done here is I've used an example of a recent DDoS incident which occurred at one of my customers just a few weeks back, and based on that, I'm sort of trying to discuss the threat and the implications and the considerations for the NOCs defending against them. So to describe the incident, I'm going to call the customer here Incident Inc. They're a hosting provider, and they host websites, bare metal servers, e-commerce. They're genuinely hosting provider setup. They have a dedicated NOC, which is a team of network engineers and a few security engineers, but mainly network engineers. So they work closely with us to augment their DDoS defense capabilities. So much so that our SOC gets the same alerts as their NOC does. So a few weeks back, we detected an incident from the on-site alerting system, as we do so often. We can see that the straight up that the incident, where the attack was targeting, who was the target within their network, and we know the volume of the attack, and then we can sort of delineate, looking at the attack message itself. It is a multi-vector attack, i.e., there are multiple vectors, multiple protocols involved. So on a very high level, you can see there's a reflective CLDAP, connectionless LDAP. You could see that there's a service flood to HTTP on port 80, which is a SYNAC service flood. And then you can see that there's a bit of a reflective NTP within there. So just looking at the alert, I can tell that it is a attack that was mitigated, but I still look at the allowed traffic. So just going by the S flow, so the majority of is blocked, and there's a little bit which is allowed through to those target IPs. So looking into the allowed traffic, I can see that the allowed traffic is not the attack traffic, and it looks like ACK to the ephemeral ports with high PLN looking like a download to me. And then I just see ACK responses to the normal HTTP. So this kind of brings me towards an incident, a segue towards the incident lifecycle. So when we encounter multi-vector or multi-protocol DDoS attacks, which are becoming more common these days, what you would see is the attack surface. What is the objective of the attacker, right? Now here, coming back to the Incident Inc.'s incident, we see that there is a sharp increase in the traffic. I.e., the objective is to take something down, to take a network down, to reduce the availability, to reduce the uptime. So booter sites, there are multiple attack tools out there, which are DDoS for hire basically, and attackers do hire them. And then they input the targets and define the timeline of when the attack is going to be, and how much, it depends on how much they pay, etc. So coming back to this attack, we can see that a lot of /24s are getting attacked, and initially we only saw this reflective CLDAP, but here looking at this, I can also see some service flood to the remote desktop protocol, some ICMP in there. So again, this is somewhat common, by the way, in an attack lifecycle, where attacks starts off as small and then kind of increases. That's what I call the dance of DDoS vectors. So they do change. So the booter sites or the attackers know what works and what doesn't, right? So they do change and they do adopt to see, if the attack is being successful. But then they do have a certain amount of compute power. So they kind of, if nothing is working and the website's still up or the service is still up, they will then just throw the kitchen sink at it. So this attack is ongoing. If we see this is 7-8 minutes down the line, we see more vectors in there. So we see increase in CLDAP. We see a bit of fragmentation. Now the fragmentation is occurring. That is occurring because the CLDAP traffic that's coming into the pipe is getting fragmented, i.e. the reason for the fragmented attack. So that's the trailing fragments from the CLDAP traffic. We then see service floods. They're far too many to go through individually, but there are various service floods. So the attackers are trying different things. We can see a reduction in the NTP traffic. So obviously, the attackers are trying different things. They're trying different service floods, etc. So this is again somewhat common. Now I want to take a quick pivot from here into the attack analysis itself. So I've been using these terms. So I just want to describe what this attack consists of. So the reflective CLDAP. So LDAP is the Microsoft lightweight Discovery Active Directory protocol. That's been on for years and years. CLDAP is a variant of that. It is sort of an alternate to the LDAP protocol. CLDAP is connectionless, and it uses UDP port 389 as opposed to TCP 389. Now, what the attackers do is they are very savvy in creating databases, right? So what we see is there are some sites, I'm not going to name them, but you can easily Google them, which provide a database of reflective services on the internet, right? And what these attackers do, they rely on those sites, but they also create their own databases. So what we see on the field is targets getting SYN packets, literally SYN packets, right? Which we call aggressive SYN scans. So entire /20s, believe it or not, of a customer, I can see every single IP address is getting a SYN. So what these guys are doing is they're waiting for a SYNAC, right? And once they get a SYNAC, they add that in a database. So it's not in my slide deck, but very recently there was a SYNAC attack, which got a lot of publicity. And a lot of the reflectors are what we have seen. So these are genuine, could be web servers, it could be your firewall port, it could be something that responds to the SYN which is coming from the internet. And what these guys do is they create a database of such reflectors. That's what I'm calling open reflector here. Now, this is not contained to just TCP. UDP is far higher in the amplification side of things. So just amplification is basically, you send a packet, you send a request, and the response comes back. The response is generally higher than the request in. So if I'm going back to connectionless CLDAP, what I'm seeing there is, traffic coming in, and the request going into these open reflectors with a spoofed IP address. So the spoof IP is the victim IP, right? So the attackers are throwing in the traffic, victim IP is being spoofed, and the reflectors are then bouncing off the attack in their response to the genuine victim. So as you can, I did a quick key in there. So the CLDAP in our research suggests the amplification factor is 46 to 55 times. With NTP, it could be up to 556 times. With Memcache, we found it could be from 10,000 to 50,000 times the original request packet. Direct attack or a service flood is slightly different, right? It's not as advanced as bouncing off a real server. In this attack, what's happening is the attackers are using some kind of attack tools to send as many PPS as possible to the victim, right? Now, this could be just SYN packets, this could be just UDP, 389 packets, it could be anything like that. And so much so that my research suggests that in the last 3 months, over 25, 1 in 4 attacks are some sort of SYN floods. Very common, booter sites use it, all the attack tools use it. The real difference between identifying a reflective or a service attack lies in the analysis of the TTL. I will show that in a second. So here you can see, this is from that Incident Inc. incident, right? Here you can see that there are SYNAC packets there. You can see the source IP addresses. They're all different source IPs. But look at the TTL. The TTL is all the same. The PLN all the same, right? And the TCP window in hex is 0040. So this is a hallmark of a scripted attack. There is a script that's sitting somewhere that's generating that traffic, right? Whereas, when you see the reflective attacks, there's a difference, right? These are real servers. Because they're open reflectors, these guys are sending, the attacker is sending them requests. These guys are sending responses back. But because they're real servers, the responses vary. What I mean by that is you can look at the p-length. So if in the CLDAP attack, if the attacker is saying, give me your user info, and if the server is saying, give me authentication, that response will be just 60 bytes, right? But if the reflective server is not, if it's not protected properly, it might actually give that information. So the response might be 1500 bytes. You see, so that's like the real amplification factor, and that's why it's different. So the TTL to the PLN to the SIP ratio gives us the ability to delineate between these two. Incident conclusion, I'm just going to speed up a little bit here. Incident conclusion, so the attack lasted for around 20 minutes. It peaked, there's a plateau there for about 6 minutes. And it got mitigated and it ended. Which is somewhat common of the attacks. Usually, so much so that the last year that we published our trend reports, 81% of the all attacks we saw was under 10 minutes. So they were like quick in and out. So the philosophy of the attacker is, they don't want to run a very large attack if they can achieve the objective in small attacks, right? Because running a large attack means getting detected, getting the risk of their methodologies being detected, then someone taking them down. So they try to, they're intelligent, and what they're trying to do is they are trying to use the less compute power, but they want to do that in small frequencies to disrupt services. Incident Inc., so the attack ended. So the question is, was there a risk of link saturation? The answer is no, because in Incident Inc.'s case, they had a lot of bandwidth. But what happens to a customer who does not have a lot of bandwidth, right? So the consideration of the NOC should be, so if I only have a 10 gig pipe, right, and the attack is 80% of that, what happens to the good traffic, right? So my good traffic only now has 2 gig, for example, to go through. So I put a caution in there that, increase in attack may mean good traffic being squeezed out. So we then sort of consider, upstream approaches. One of the upstream approaches is, FlowSpec, BGP, and LRI advertisements, where you can granularly sort of send an BGP advertisement to your upstream to say, so in this diagram, I've got my, the platform is sending an update to the upstream saying any, for example, UDP traffic towards that subnet, right? UDP layer, you can do sort of layer 3, layer 4. So any UDP traffic towards that subnet, just black hole it. So what that means is, not all traffic is getting sort of discounted or dropped at the upstream. Just the traffic which is problematic is getting dropped at the upstream, and the good traffic is still coming in. Well, TCP traffic is still anything that is not UDP is still coming in. So a fraction of traffic comes in. Now, So that kind of gives you, a slight granular relief of this kind of attacks. The only thing to note here is implementation may vary, right? So vendors vary in terms of how they implement FlowSpec at the moment. Another consideration is RTBH. It isn't sort of an option of last resort, but people do take it. This is where you take a destination IP address and a /32 or even a /24, /128 and IPv6 and just say upstream, I don't want that traffic at all, right? So any traffic, good or bad, will be dropped. And you have a period of withdrawal. So you say, withdraw it after 7 minutes, for example, or 10 minutes or 15 minutes. And then you recheck, you re-verify if the attack's gone. The idea there is that, you do not want to see the any traffic to that depth because you don't want to hurt, you don't want to cause collateral damage, you don't want to hurt anyone else. The question there is, what happens if that's a connected IP? There are hundreds of customers behind that. So there's a consideration to be done, but then, that's a balance that the NOC or the organizations have to make. In my example, my customer did not have to do this. So the takeaway, quickly concluding the presentation here, again, as we've specified earlier, detection is the key of the discrete attack vectors. As soon as you know them, as soon as you classify them, you can then mitigate against that. Consideration is, the attackers are smarter. They don't want to use their compute resources all the time. So consideration towards, do you mitigate all the time? Do you have an always-on sort of mitigation platform? Or do you sort of react to it? So, proactive versus reactive. And then what's the cost for the business for that? And finally, smart alerting. So how does NOCs make those decisions? You enable the NOC to make that decision with the help of smart alerting, reporting, etc. For example, we rely on autonomics and reporting, smart alerting for doing that. Finally, I'm literally concluding here. Again, sub-second detection and mitigation equals high time, and getting the reports into the NOC to the business is pivotal. It's extremely important, and that gives the ability for NOCs in the business to make the right decision in terms of how they want to mitigate an attack. Finally, if you have any questions.
Yep.
Tom Strix, Cloudflare. I was wondering, how much do you think part of it is also the responsibility of ISPs and origin networks to do source filtering?
There's definitely that's an excellent question. How much is the responsibility upstream to do the source filtering? At the end of the day, that depends on the service level agreement that the customer actually have with the upstream. Now, for example, the RTBH, the remotely triggered black hole that we discussed earlier, a lot of upstream ISPs which I've come across, they give you a community, for example, right? They say, you know what, there is a community, and if you do want to advertise an RTBH, use that community. So, for example, a customer can say, you know what, I want to do that. One of my destination IP addresses or one of my subnets is getting attacked. I will use your community, and I'll send an advertisement to you to do that. And there are quite a few service providers which I've come across do that. The other aspect is FlowSpec, right? Because FlowSpec, again, it implements, the implementation varies by the vendor. So I think I've said that in the slide again. And the vendor, there must be an agreement between the customer and the vendor or the service provider in terms of how would they accept the FlowSpec, right? But realistically, 90% of attacks is or over 81% of attack that we saw in the trend reports were, less than 10 gigs, i.e., they were manageable at the enterprise level or at the customer edge level rather. So again, depending on the attack itself, and what agreements you have with the customers.
The point I was trying to get at is that all of these attacks rely entirely on spoofed IP addresses. Either you're spoofing IPs to a reflector or you're directly spoofing to whatever, right?
Yes.
Isn't it the responsibility of whatever service is generating that spoofed IP packets to not allow spoofed IP packets on their network? That was the point I'm trying to get at.
Right. So that is true in case of the direct or the service floor attacks. However, in the open reflector attacks, in reflective attacks, the reflectors themselves are the real IP addresses.
Oh, yeah,
but
definitely.
But the request that is coming in, that is spoofed.
Yeah, they're still relying entirely on spoofing. So just if you're an ISP or if you're a content like OVH or whatever, just don't allow spoofed IP traffic on your network and the problem goes away. Because we're not going to get rid of UDP anytime soon and then fix the problem elsewhere, right?
Yeah, so again, the question then becomes the agreement that the ISP has, the service provider has, is how do they then do the delineation themselves? And so there are trillions of packets are going through their network, right? So they then have to have the compute resources in place. So who's paying the cost? The question is almost always of the cost. Who is paying the cost? So is the cost being paid by the customer? So is the cost then distributed to the end customer? Again, every time you compute a packet, there is a cost to that, right? And then if you're doing that trillions of times, now who's doing the cost? So it's an excellent question, but yeah, that does require some consideration. Why and how the business model business community can accommodate that. Absolutely, good question.
Any more questions? Last call. Okay. Thank you very much, Aseem.
Thank you. Thank you, guys.